Hi again. It is time to train our model. Since this is an iterative problem, we must create a loop which will apply our update rule and calculate the loss function. I'll use a for loop with 100 iterations to complete this task. Let's see the game plan we'll follow. At each iteration, we will calculate the outputs and compare them to the targets through the loss function. We will print the loss for each iteration so we know how the algorithm is doing. Finally, we will adjust the weights and biases to get a better fit of the data. At the next iteration, these updated weights and biases will provide different outputs. Then the procedure will be repeated. Alright, time to create the outputs. They are given following the well-known linear model equation. The outputs are equal to the inputs times the weights plus the biases. Multiplying matrices requires the dot method. I'll use the NumPy one. So, np dot of inputs and weights. Now, the dot product of the input times the weights is 1000 by 2, times 2 by 1, so a 1000 by 1 matrix. When we add the bias, which is a scalar, Python adds it element-wise. This means it is added to each element of the output matrix. Okay. For simplicity, let's declare a variable called deltas, which will record the difference between the outputs and the targets. We already introduced such variable in the gradient descent lecture. Deltas equals outputs minus targets. That's useful, as it is a part of the update rule. Then we must calculate the loss. We said we will use half the L2 norm loss. Pythonically speaking, deltas is a 1000 by 1 array. We are interested in the sum of its terms, squared, following the formula for the L2 norm loss. There is a NumPy method called sum, which will allow us to sum all the values in the array. The L2 norm requires these values to be squared, so the code looks like this: np.sum of deltas squared. We then divide the whole expression by 2 to get the elegant update rules from the gradient descent. Let's further augment the loss by dividing it by the number of observations we have. This would give us the average loss per observation, or the mean loss. Similarly, to the division by 2, this does not change the logic of the loss function. It is still lower than some more accurate results that will be obtained. This little improvement makes the learning independent of the number of observations. Instead of adjusting the learning rate, we adjust the loss. That's valuable, as the same learning rate should give us similar results for both 1000 and 1 million observations. Once again, that's something we'll discuss in more detail later in the course. We'll print the loss we've obtained at each step. That's done as we want to keep an eye on whether it is decreasing as iterations are performed. If it is decreasing, our machine learning algorithm functions well. Finally, we must update the weights and biases so they are ready for the next iteration. Using the same rescaling trick, I'll also rescale the deltas. This is yet another way to make the algorithm more universal. So, the new variable is deltas underscored scaled and equals deltas divided by observations. Let's update the weights. We will follow the gradient descent logic. The new weights are equal to the old weights minus the learning rate times the dot product of the inputs and the deltas underscored scaled. The shape of the weights is 2 by 1. The shape of the inputs is 1000 by 2, and that of the deltas scaled is 1000 by 1. Obviously, we cannot simply multiply the inputs and the deltas. This is an issue that may arise occasionally due to the linear algebra involved. To fix it, we must transpose the inputs matrix using the object.t method. Now, the matrices are compatible. 2 by 1000 times 1000 by 1 is equal to 2 by 1. I'd like to spare an extra thought on that. Often, when dealing with matrices, you find the correct way to code it through dimensionality checks and compatibility errors. However, transposing matrices doesn't affect the information they hold, so we can do it freely. Alright, let's update the biases. The new biases are equal to the old biases minus the learning rate times the sum of the deltas, as explained in the gradient descent lecture. This is the entire algorithm. Let's recap what it does. First, it calculates the outputs for given weights and biases. Second, it calculates a loss function that compares the outputs to the targets. Third, it prints the loss so we can later analyze it. And fourth, we update the weights and the biases following the gradient descent methodology. Let's run the code. What we get is a list of numbers that appears to be in descending order, right? These are the values of our average loss function. It started from a high value, and at each iteration, it became lower and lower until it reached a point where it almost stopped changing. This means we have minimized or almost minimized the loss function with respect to the weights and biases. Therefore, we have found a linear function that fits the model well. The weights and the biases are optimized, but so are the outputs. Since the optimization process has ended, we can check these values. Here, we observe the values from the last iteration of the for loop, the one that gave us the lowest loss function. In the memory of the computer, the weights, biases, and outputs variables are optimized as of now. Congratulations! You learned how to create your first machine learning algorithm. Still, let's spend an extra minute on that. I'd like to print the weights and the biases. The weights seem about right. The bias is close to 5, as we wanted, but not really. That's because we used too few iterations or an inappropriate learning rate. Let's rerun the code for the loop. This will continue optimizing the algorithm for another 100 iterations. We can see the bias improves when we increase the number of iterations. We strongly encourage you to play around with the code and find the optimal number of iterations for the problem. Try different values for observations, learning rate, number of iterations, maybe even initial range for initializing the weights and biases. Cool. Finally, I'd like to show you the plot of the outputs at the last iteration against the targets. The closer this plot is to a 45-degree line, the closer the outputs are to the targets. Obviously, our model worked like a charm. Alright. This was the last lesson from our first big topic. From next on, we will start with more complicated stuff. If you have any doubts about your knowledge so far, please revisit the lessons and make use of all the extra resources available, like course notes, exercises, and Jupyter notebooks. In addition, feel free to post in the course Q&A section. We love hearing from you. Oh, and one more thing. If you like the course so far, please leave us a review. It helps a lot. Thanks for practicing and thanks for watching.